Good morning, everybody. Let's try it from home. I hope it works. Please confirm that you can hear me and you can see my screen. Hello, can you see my screen?
Yes.
Okay, perfect. So I would like to begin by recalling some things that I will need today. So first we'll use this theorem that if E is a finite graph, this includes the empty graph, it's also all right, that the space of all finite paths in this graph is finite if and only if there are no loops in E. Okay, it was one of our first theorems proven in this course, and we are going to use it today. And there is another one which we are going to need. It's a proposition about connectedness. No, sorry, it's a proposition about arrangement of vertices in order to get things upper triangular. I think 128. Okay, and it's not just the proposition. No, sorry, this is this is still counting paths. That's not what I want. It's in adjacency matrices. Yes. Yeah, that's, I think, yes. This is proposition 138, and not just that we will need the claim, which is right here, but we'll need this fact from the proof. So remember, this wasn't so completely trivial proposition, which claimed that if I have a finite acyclic graph, so these are assumptions, a finite acyclic graph, then I can always order E0 in such a way. And now the claim is about the adjacency matrix. Okay, now we're going to do something similar, but it's not the adjacency matrix. But the point here is that we constructed a partial order, actually the total order in this finite set of vertices with such a property that there exists there exists a path from a vertex, sorry, an edge from one vertex to another one, if and only if this vertex from which an edge starts is less or equal to a vertex where this edge ends. Okay, and that's what we managed to do. That we managed to construct such a total order, and this reasoning here was not so completely trivial. So I want to use it now in my proof. Okay, so these are two facts which I'm going to use: the existence of a special order in the set of vertices, total order, and the fact that if I have a finite graph, then this is a cyclic if and only the space of all finite paths is finite. Okay, so now I can stop sharing this screen. I can go now to share my whiteboard, and we'll start writing. Okay, I have to arrange everything here. Right, for starters, I would like to make certain, not corrections, but I would like to add some things to what we discussed last time. So remember, we are talking about simplicity of matrix algebras, and that they have no non-zero proper ideals. And in fact, the same is true about the infinite matrix algebra. So let me remind you what it is. I have M infinity of K. This is by definition the union over all, say, natural numbers without zero of K, Oops, I have a lot of junk appearing. Eraser. Where we're making sense out of this union. So where the union is defined via the inclusions of say, n by n matrices into n plus 1 matrices in the following fashion. You have a matrix M, and which is n by n, and you view it as an n plus 1 by n plus 1 matrix. What happens? All of a sudden, my screen went black. And I have a message, my Zoom is not responding.
We hear you, but we have, maybe not we, maybe I only.
Yeah.
The picture stop.
Stop. Yeah. Well, I mean, I have a message that Zoom is not responding. I have a blue circle turning around, and there is nothing. Yeah. Well, now it appeared. Okay. I don't control it. Sorry about this. So I view an n by n matrix as an n plus 1 by n plus 1 matrix. Well, in the obvious way, I put m in the upper left corner, and I put zeros around. Okay. So this is what makes sense out of the union, and this space of infinite matrix algebra is in fact the algebra of all finite matrices. So M infinity K is the algebra, non-unital, of course, of all finite size matrices. And this algebra is also simple. And to prove it, it's a new exercise. Well, you have to modify proof a little bit because this is a non-unital algebra. And basically, you prove it by showing that absolutely all elementary matrices, so the linear basis for this matrix algebra, will be in any non-zero ideal. So you start by assuming that you have a non-zero element in your ideal, and then you prove that if it is a two-sided ideal, then in fact you can get an elementary matrix. And because elementary matrices still give you a basis of this M infinity of K, this way you prove that there are no proper non-zero ideals. But this is your exercise, and I simply wanted to add this infinite matrix to our collection of matrix algebras, because the simplicity claim, the claim that it cannot be the path algebra, works as well. Okay, because it's non-commutative, of course, and it's simple, whereas we know that all non-commutative path algebras are not simple because they have non-trivial row ideal, which is a proper non-zero ideal. And by the way, a remark, many of you are more than aware of it, that if you take a norm closure of this algebra, you get the sister algebra of compact operators. And this is actually very interesting that in between these two guys, so all finite size matrices and the sister algebra of compact operators, but in between, you have a plethora of very interesting ideals. So K is a simple sister algebra. So it doesn't have any proper closed ideals, right? So the only non-zero closed ideal in K is K itself. But there are plenty of in-betweens, for instance, Schatten ideals, Marcinkiewicz ideals. See, this is where things are getting interesting. So this is very important in index theory. So people who do non-commutative geometry, like Sophie, for instance, they know it very well. And this is a general recipe. If you maybe not recipe, phenomenon. If you look, for instance, at this vector space, which is very algebraic, you take a field, okay, and you take, say, countably many copies of this field. All right, that's an infinite dimensional vector space, but it has countable bases. And then you have something huge, the product also over all natural numbers of a field. Now, this is a gigantic vector space, right? Because here you have absolutely all sequences, and here you have only finite sequences. But the point is that in between, exactly in between, you have interesting things. You here have these Banach spaces, Hilbert spaces. Okay. So interesting things happen in between some extremes, right? And I would like you to bear in mind this phenomenon. But all we needed, this is just a remark, I don't need it in my course. I just wanted you to know that M infinity of K also simple algebras, so they will figure in our summarizing corollaries from the theorem that we proved last time. And in fact, this norm completion here, this is exactly a process of completing a Leavitt path algebra to a sister algebra, okay? So M infinity of K, well, say, let's take complex numbers, okay? So here, well, I wrote K, but if I claim it to be a sister algebra, well, I better take complex numbers. So this will be the Leavitt path algebra over the field K of this infinite path graph. And the compact operators, this is a graph sister algebra, well, of the same graph. So the norm completion of all finite side matrices, non-unital algebra, into the sister algebra of compact operators, this is precisely an example of a completion of a Leavitt path algebra into a graph sister algebra. So we will do it. So we'll do such a thing later on. Okay. What next? So now the corollary that we had before can be boosted. We can say that, let me write it down, I said it, but let's write it down. The matrix algebra M and K. And now I write N running from 2 to infinity. Infinity is included. Cannot be isomorphic to the path algebra of any graph. Okay, the reason is exactly as before, because M infinity of K, which is now included in this corollary, is non-commutative and simple. Okay, And now we can have some corollaries of our theorem. Remember, we proved a very strong and I think very beautiful rigidity theorem, which tells us that if I take a direct summand subalgebra of my path algebra, then in fact it's again the path algebra of a subgraph of a graph of which I took the path algebra. So first corollary, we immediate corollary of the theorem that we proved before. And it's worthwhile, as I wrote in my email, it's worthwhile to have a look at the proof as it's written right now, because I clarified many issues and I smoothed it out. So now I think it's more transparent than it used to be. I'm wondering about the color. Can I change the color into something different? I don't know, brown. This green is a bit too shiny to me. Okay, so first corollary that we didn't manage to discuss a week ago is the following. The path algebra, okay, oops. The path algebra AE decomposes into a direct sum non-zero subalgebras if and only if is disconnected. So this is the immediate corollary of our theorem, because, well, we proved, of course, much more than just this, but in particular, we proved that K of E is then isomorphic to K of E1 plus K of E2, and E simply decomposes into two disjoint subgraphs. And then we have a lemma, which was proven, I think, by Davide. So maybe I'll write proof. E is disconnected if and only if E decomposes into the disjoint union of its subgraphs. Okay. So this is what we proved in our theorem, and that you have this decomposition into direct sum of non-zero subalgebras if and only if the graph decomposes like this. And then we have a lemma of, and we should write E1 non-empty and E2 non-empty. And this was proven, I think, by Davide, where this is tantamount to E being disconnected in the sense that between any two different vertices, there is an unoriented path. Okay, so this is how we get this corollary from our theorem. And we also have a summarizing corollary, which in fact is very important, because this is what tells you a lot about the structure of path algebras, of what they cannot be. So this is the corollary of our, you see, how do I go back? Yes. So if you combine our theorem with this corollary, So we know that the matrix algebra for any n from 2 to infinity cannot be a path algebra. If you combine it with our rigidity theorem about the decomposition of path algebras into direct sum of its non-zero subalgebras, we can now write the following corollary. A non-commutative matrix algebra M and K, now with n running from 2 to infinity, infinity included, cannot be a direct summand subalgebra of any path algebra KE. What's going on? Okay, and how do we prove it? So suppose that we have a path algebra KE and that it decomposes into M and K, direct sum with some algebra A. Okay, this is as algebra. So this is what I mean that M and K is direct sum and subalgebra. And when I say as algebras, it means that the multiplication of the right-hand side is component-wise. In particular, M and K times A is equal to 0. Then, if A is equal to 0, we have a contradiction by our corollary. Right, let me make it clear. I mean this corollary, the green corollary. Matrix algebra M and K cannot be isomorphic to the path algebra of any. Okay. If A is not 0, well, then we have a non-trivial decomposition of KE into non-zero subalgebras. And by the theorem, both of them must be path algebras of a certain graph. So if A is not 0, we get a contradiction by combining the theorem and the corollary. Right? And this is as far as we go, but somehow this is a point at which I would like you to realize that path algebras and sister algebras are completely at odds. Okay, remember that this is just a remark, that when you have any sister algebra, then by Gelfand-Naimark theorem, you can always embed it into operators on some Hilbert space. And you can always take all irreducible representations of A, and basically you can view A as some kind of direct integral of all these irreducible representations. And then you can think, this is very rough, I'm speaking between inverted commas, it's just about the intuition, it's not rigorous. You can think about these as some infinite full matrix algebras with appropriate completions, okay? So you can think about any sister algebra as this kind of direct integral of full matrix algebras, and that's the kind of intuition. And such an algebra, it cannot be a path algebra, because you see, in particular, what I showed you is that I cannot take some direct n say ni, some direct summons of direct sum of algebras, well, because of the corollary that we have. Okay, so path algebra not only cannot be a matrix algebra, it also cannot be a direct sum of matrix algebra. So this is very far away from sister algebras. And if you would be finite dimensional, well, then there is no completion. Any finite dimensional sister algebra is precisely a direct sum of full matrix algebras. Okay, then there is no completion involved, and then this is rigorous. I don't need anything anymore. I know that K of E cannot be a finite dimensional sister algebra, because then it would have to have a non-commutative, I mean, except for just complex numbers, right? Of course, this is a sister algebra, and if I take the path which has only one vertex and no edges, well, then this is the same thing. Okay, so this is M1 C. But that's it. This is the only place where they meet. If you take any non-commutative finite dimensional sister algebra, then this will be a direct sum of matrix algebras, and at least one of them will be non-commutative, and this will contradict the corollary which we just proved. Okay, so this is a very strong result about the direct sum. But a non-commutative matrix algebra cannot be a direct sum subalgebra of any algebra. Okay, so you see, our going into constructor relations and Levi path algebras from graph algebras is actually necessary if we want to enter the realm of sister algebras. Path algebras and sister algebras are adults. But as I already told you, it's not really path algebras that people are so interested in, but in algebras that you get as quotients. So the name of the game is to study appropriate ideals in path algebras and then the quotient algebras. Okay, so this basically finishes the lecture from a week ago. Oh my God, in order to half an hour. Now we can proceed further on. Do you have any questions concerning these decomposition theorems? Okay, no questions. So we proceed further. And I want to show you a certain simple proposition which I missed. I should have told you this already in my previous lecture about path algebras, but I missed it. It's a very, very simple proposition which bundles up families of interesting examples. So let me do it right now. And I took it from the blue book of Asem, Simpson, Skowroński. So let E, and here I will use my ordering claim, right? That I can order the space of vertices in such a way that I will have paths only from a smaller vertex to a bigger vertex for this order. So let E be a finite cyclic graph. And remember this proposition which I showed you and its proof was exactly done under the same assumption. E was assumed to be a finite acyclic graph. And I want to be explicit, so with the notation for indices, so let me write it down with E0 being the set from V1 to Vn. Okay, then it's path algebra KE. Is isomorphic to the upper triangular matrix algebra of the special form, the upper triangular matrix algebra. And now I need a little space, and I've got a little space. Let me baptize this algebra as upper triangular for the graph E over the field K. And the definitions as follows. Well, it is really upper triangular, so have 0 below the diagonal. On the diagonal, we just have fields, but they are spanned by these vertices. They have chi v1 in the first row. You have some chi vi here. And you end up with k times chi vn here. Well, in this corner, you'll have chi v1, the path algebra chi vn, and so on and so forth. And generically, you will have chi vi, ke, chi vj for I less than j. Okay, so maybe I'll write it down somehow. Here, chi vi.
KVN in the
And of course I said and thank you, Anya. I said n and I wrote 2.
Okay.
Yeah, thank you, of course, yes. So chi vi ke chi vj. So well, this is not in the last column. This is somewhere, you know, in the middle. Yeah. And this is something which is inside, of course, the following matrix algebra, the upper triangular matrices of size n with entries in the path algebra ke. Well, you can view, well, this is a simple identification you should remember from high school. If you have the algebra of matrices with entries in another algebra, then you can write it down as a tensor product. Here I can just take it as the definition. So I take the usual algebra of upper triangular matrices over the field K, and I tensor product it with the path algebra. Okay. Sorry, I wrote it vertically, but you know what I mean. Okay, and now let me make sure that the notation is obvious. So let's make it crystal clear here. The off diagonal entries are from chi I. Essentially, the whole path algebra between these two vertices, these two projections, chi vi, chi vj, for I less than j, ij running from 1 to n, and 0 otherwise. And by otherwise, I mean for I bigger than j. And on the diagonal, you saw it. These are just fields on the diagonal, but these are actually one-dimensional vector spaces with a basis being chi of vi, where vi is one of my n vertices. Okay, so I think that now this is clear what I mean by this algebra. There's a certain subalgebra in the tensor product algebra of the upper triangular n by n matrices and the path algebra K of E. Okay, so this is what I want to prove right now. So for starters, note that by the proposition which I showed you, well, actually by the proof of the proposition, there exists a total order in my set of vertices such that if there is an edge from vi to vj, then I is less than j. Okay, there cannot be an edge from vi to vi because we assume that the graph is a stick. Okay, so now it immediately follows that the same is true if I replace an edge by the path. Okay, so maybe I'll just erase it. And right here, sorry, I also have to erase this. And again, I have a zoom problem. Wait for the program to respond. Using a different computer than at home. And of course, I just have the usual home internet connection. It's not the super fast connection at IMPAN.
So maybe the camera off would be.
Yeah, you're right. Anya, you're right. I can kill the camera. You cannot see me anyway because I I'm sharing the screen, but now I cannot. Yeah, okay. So you are telling me, Anya, to switch off. How do I do it? I still have wait for the program to respond. There's nothing I can do. Oh, yes. Okay, I better not try it right now because it's, oh, I still have a game problem. Please move this window away from the shared application. Ah. Okay, such that if there is a path from Vi to Vj, then I is less than j. Not position, proposition, sorry. Well, right, and it's obvious because if I have a path from Vi to Vj, well, when a path consists of edges, and I go from vertex Vi to some vertex Vk by the first edge, and of course I is less than k, and so on and so forth. And by the transitivity of the inequality, I get when I must be less than j. Now, this is really immediate, but it's crucial. You see, when you read this proposition in the blue book, Asem, Skowroński, Simpson, then it's taken for granted. They said, okay, let's assume that something happens. But you saw this proposition, this proof is actually quite non-trivial, that there exists such a total order, okay? And we are making certain assumption, but this is an assumption, this is so-called WLOG, without the loss of generality, okay? Because we can always choose such order, we can assume without the loss of generality. So hence, without the loss of generality, in other words, this is a vacuous assumption. It's an assumption we can make because it's always possible to arrange our vertices in such a way that the property that we desire is satisfied. So hence, without the loss of generality, the loss of generality, we can assume that a set of vertices is ordered precisely like this. Yeah, and precisely like this, meaning that this order between vertices is such that if there is a path from Vi to Vj, then I must be less than j. So in particular, there is no path whatsoever from Vi to Vj if I is bigger than j, or actually if I is bigger or equal to j. So you can write no paths Vi to Vj for I is strictly bigger than j. And when I is equal to j, then the only path is a zero-length path of the vertex itself. Okay, so this is the first part, which relies on the previous semester. And by the way, I didn't mention it, but I hope it's obvious to you that when you look into these animals, chi vi sandwiching, I mean the path algebra ke sandwich between chi vi and chi vj, then these are simply, this is simply the subspace of the path algebra spanned by all paths that start in vi and end in vj, all right? Because all other paths are killed. I mean, chi's labeled by paths that do not start in vi and do not end in vj are killed by the sandwich. Okay, I think it's clear. But it's a neat way to write it down. Okay, so now yes, so in fact, what I wrote in parentheses, I can write down in a better way. So let's do. Actually, I'll just put a comma here, and we go to the next page. So chi vi sandwiching ke chi vj is equal to 0. Okay. Next, observe that since chi's give me a basis of a path algebra, we have the following direct sum decomposition. And this is not a decomposition of algebras, okay? This is the decomposition in the sense of vector space. I have this big direct sum. Here I have my heroes, which are chi vi ke chi vj. And here I run my indices. So first I have I less than equal than j, and then I have ij running from 1 to n. Okay? I hope it's clear. Well, you simply have 0 when you look at chi vi ke chi vj for I bigger than j. This is why I can restrict myself to I less than equal than j. And the other thing is obvious. Remember that our path algebra is spanned by finite paths, and every finite path must begin somewhere and must end somewhere. So I can simply write my space of all finite paths as the disjoint union of all paths that say start at the vertex vi and end at the vertex vj. And then I run I and j through the numbers from 1 to n, right? This way I write FPE as the disjoint union of such n squared subsets. And here I know that some of them are empty. That's why I exclude I bigger than j. And I take the linear span, right? So I take the linear span given by paths that start at vi and end at vj. And this is exactly what this sandwiched vector space stands for. So this direct sum decomposition is obvious simply by the fact that chi's labeled by finite paths give me, by construction, by definition, a linear basis of my path algebra. Okay. And right, we already said it, but it's worth writing it down. But as there are no loops, we know that the sandwich chi vi ke chi vi is just equal to k chi vi. Right, because here the loops, the only positive length paths that could survive would be the loops based at vi, but they are not allowed, loops are not allowed. So the only path starting at vi and ending at vi is the vertex vi itself, okay? And of course, I runs from 1 to n. But now it's completely clear that we have a natural linear map from our path algebra KE to this algebra of upper triangular matrices, okay? Which is a linear isomorphism. This is obvious by construction. So hence, the natural linear map F from KE to this UT EK given by sending chi P to EIJ tensor chi P. Remember that I defined this algebra, this upper triangular algebra UTEK as a subalgebra in the algebra of upper triangular matrices over the path algebra, which is the tensor product algebra of upper triangular matrices and the path algebra. So this is how I'm using it, all right? It's important that you understand the relationship between ij and p, but you can easily guess it. Vi is simply S of P, and Vj is T of P. Okay, so the path P ends at the vertex Vi, sorry, starts at the vertex Vi and ends at the vertex Vj. And then I take the elementary matrix Eij. So remember the elementary matrix Eij, this is a matrix which has zeros everywhere, except that in the ith row and the jth column, it has a 1. Okay. And this is, of course, a basis of our matrix algebra. So I didn't finish the sentence, hence the natural map is an isomorphism. Right? Because if you look at this vector space decomposition and then compare it with the definition of our algebra, you see that this is the same kind of a decomposition. When you look at this upper triangular matrix algebra as a vector space, well, then this is a direct sum of the vector spaces which are written as entries of this matrix. And this is precisely the same direct sum as we wrote here for the path algebra. Okay. So as vector spaces, they are obviously the same. And the identifying map is just that you have to put appropriate pieces in appropriate parts of your matrix. And this is precisely given by this formula. If I have a path that starts in Vi and ends in Vj, then this direct sum and piece is put in the part of the matrix, which is ith row and jth column. Okay, so that's exactly the identification formula. And as a vector space map, this is an isomorphism. So to finish the proof, to verify that this is an algebra homomorphism. And then it is an isomorphism of algebras. And we take a path Q, define Vk to be S of Q, the beginning of the path Q, define VL to be the end of the path Q, and compute. When I'm touching the screen with my hand, it creates some junk on it. Okay, so let's compute it. Of course, it suffices if I do it on the basis elements, all right? So I take a path P and I take a path Q, and I compute f of chi P chi Q. But of course, for starters, I know that this is the Kroneker's delta Jk. Remember that we already have notation for P. We know that Vi is the beginning of P and Vj is the end of P. So if these two paths are to match in order to create the path PQ, then I must have that Vj is equal to Vk. So in other words, J is equal to K. Hence this Kronecker delta Jk. If J is equal to K, because otherwise we have 0. Otherwise, if the end of P is not the beginning of Q, then by definition, this multiplication in the path algebra will give me 0. And f of 0 is 0. So I write this Kronecker delta here, and now I can write f of chi PQ. And now I can apply this formula. So remember that the path PQ begins where path P begins, which means VI, and it ends where the path Q ends, which means VL. So by our formula, we know that this is equal to delta Jk, which I just rewrite, but here I write the elementary matrix E, I, L, tensored with chi PQ. All right, this is just the application of the formula for F. But if you remember how to multiply elementary matrices, I can just write it down as multiplication of E ij times E KL. Then it will be exactly equal to delta Jk times EIL. And here I have my chi PQ. But now again, I remember that chi PQ is chi P times chi Q. So I write it down as E ij tensor chi P times E KL tensor, sorry, this is not nicely written. Let me try again. EKL times chi Q. Right, because I already know that if the end of P is not equal to the beginning of Q, then I already here have 0. These two, then J is different from K, and these two elementary matrices will multiply to 0. So sort of the Kroneker's delta is already in the multiplication of elementary matrices. And when this product is non-zero, then I have that the end of P is the beginning of Q. So chi P times chi Q is in fact not 0, but chi PQ. Well, but then of course, this is precisely f of chi P f of chi Q. Right? Because the beginning of Q is Vk, and the end of Q is Vl. And the beginning of P is Vj, and the end of P, the beginning of P is Vi, and the end of P is Vj. So by our recipe, the first part of my multiplication is f of chi P, and the second is f of chi Q. And this ends the proof of this proposition. right? This is an elementary proposition, no thrills, but it gives you lots and lots of examples, really. I mean, now you can specify. So in particular, note the following. So if E is a graph, of course, finite acyclic graph, the finite acyclic graph such that there is at most one path between any two different vertices, well, then we know that the sandwich is at most one dimension. Then the dimension of chi vi ke chi vj is less or equal to 1. So either we have 0 or we just have a field. Okay. So ke so ke is a subalgebra of the algebra of upper triangle matrices n by n over the field K. All right. Because now if you look into our definition of the UTEK algebra, well, I only have just fields on the diagonal. And for such a graph where there is at most one path between any two different vertices, then I know that the guys that are off diagonal are either 0 or just a field. Okay, so this will be, in fact, without this tensor product with Ke, it will be simply inside UTN of K. And you have lots and lots of examples. So for instance, let's take the following. Okay, and I can call it V1, V2, and V3. Then it's ordered as we want it, right? We have an edge from, or a path from V1 to V3, and from V2 to V3, and 1 is less than 3, 2 is less than 3. So I took my total order as desired. So now I should write a 3 by 3 matrix. I'll have K here, I'll have K here, I'll have K here, 0 below the diagonal. And we have a path from 1 to 3, so I have a K here. There is no path from 1 to 2, and then we have a path from 2 to 3. Okay, so this is a subalgebra in UT3 of K. Right, so you don't take the full algebra of upper triangular 3 by 3 matrices, but you zero the element in the first row of the second column. Okay, and that's it. This is the algebra, which is isomorphic to the path algebra of this graph. But I wanted to do this proposition. I know it's completely elementary and the proof is totally boring. But we did it in a more subtle way than the blue book, because we proved that there is no additional assumption, that we can always, without the loss of generality, pick up the total order on our space of vertices, so that we are really upper triangle. Okay. And on the other hand, if you are not under this assumption, so for instance, take E. I don't know why, but I think it's called Kronecker graph. You have just two vertices, V1, V2, and you have two edges going from V1 to V2. Then the algebra will be something like this: K, K, 0, and here you have K squared. Because we have exactly two paths from V1 to V2. And in general, this is worthwhile to remember. So by the way, if R is a ring and M a bimodule over R, then we have a natural ring structure on such upper triangular matrices: R, R, 0, M. Okay, is a ring. Why? Because look, if I have R, M, S times R prime, M prime, S prime, well, then here I'll get 0, here I'll get R prime, here I'll get SS prime. But in this upper right corner, what you will get will be R M prime plus M S prime. So the only structure that you need is the structure of a bimodule. We need to be able to multiply on the right and the left. Okay. So here we view it as as a bimodule over the vector space. So how do I multiply on the left? So A times BC is of course AB AC, and on the right BCD is BD CD. So that's the multiplication right here. And now this algebra is the path algebra of such a graph. Okay. I can give you one more example. So now if E is disconnected, well, if E is disconnected, it means that I have one bunch of vertices which are connected and another. Well, no, let's put it this way. Then I can write my set of vertices as a disjoint union of non-empty subsets in such a way that there will be no path between one set of from a vertex in one set to a vertex in another set. Okay, so I will have here one set of vertices, here another set of vertices, and there will be absolutely no path from one set to another in either direction. Okay. But this means if I look at my upper triangular matrix algebra, then it will be in the block diagonal form. Then U T Ek is block diagonal yielding a direct sum decomposition our path algebra Ke. Of course, this is finite cyclic. So I should have proven this proposition earlier, right? Then it would be like a sneak preview into our rigidity theorem. This says that, okay, if already we have something finite as cyclic, then it's actually, its path algebra is some kind of upper triangular algebra of matrices. And then if on the top of it, the graph is disconnected, then this upper triangular matrix algebra is in fact block diagonal, which means that we have this direct sum decomposition of our path algebra into the direct sum of its subalgebras, okay? But of course, we proved it in a much bigger generality, but here you can view it immediately by this isomorphism, which is elementary in this proposition. You see that a disconnected graph would give you a block diagonal matrix algebra, which of course is direct sum of subalgebras. And it's perfectly in line, it illustrates the theorem. Okay, we have 4 minutes till the end of the lecture. Now let me see what else, I wanted to tell you about. Yeah, our next step was about Jacobson radical. I really hesitated a lot how much to speak about it, but it's something which is very important in path algebras. And this is an important algebraic notion. So the way I want to do it, the way I decided to do it, is that the necessary algebraic background about Jacobson radical in general, which is not in relation with path algebras, but for arbitrary rings and algebras, will be done in exercises. So I wrote down 3 new exercises that solve some quite interesting problems related to the Jacobson radical in general. And then I applied to prove a simple proposition, actually, that if I take the Jacobson radical of the path algebra of a graph which is finite and acyclic, then the Jacobson radical is simply the arrow ideal. And this proposition is easy only because we have some general claims which are not so easy and can be proven for any algebras. But because I don't want to clutter the lecture with some general algebra, I delegated the proof of these Jacobson radical facts into the exercises. But in the remaining 2 minutes, at least, I should be able to give you the definition. So this is a completely new chapter of this lecture. Let me do it in the following manner. Let R be a unital ring. Now, a disclaimer, you can do it for non-unital rings, but then we don't need it, as I have no non-trivial claims for non-unital path algebras about the Jacobson radical. And defining the Jacobson radical in the non-unital case requires more care, and I don't want to define some concepts that I'm not going to use at all. When you are unital, you have a very beautiful characterization of a Jacobson radical. You should be aware that it's like with projective modules, like with any concept which is important in mathematics, you always have zillions of equivalent definitions. The same is true about the Jacobson radical. I picked up as a definition one of these many equivalent characterizations. I picked up the one which somehow most appeals to me, and it is the following. So R is a unital ring, and what is the Jacobson radical? The Jacobson radical, I chose to denote the J rad of R, it's by definition the following set. take all elements in a ring R, which have the property that for all x in R, there exists the inverse of 1 minus xr. Okay? So this is where we will stop for today with this definition. It looks a little bit asymmetric. Why do I choose xr, not rx? Well, that's because you can prove that in any unital ring, it's actually a very nice and non-easy exercise, that 1 minus xr is invertible if and only if 1 minus rx is invertible. So in fact, this definition is symmetric. And once you know this property, you can actually prove that the Jacobson radical of a unital ring is an ideal of this ring. Okay, but this is in exercises. And well, to finish the story about Jacobson radical and path algebras, I have to prove this proposition of what is the Jacobson radical of the path algebra of a finite acyclic graph, but this is for the next lecture. So let's stop right now and meet 11:15. I stop recording.